So this is an exercise that I asked you to look at last Thursday. All right, here's some numbers in our S20 number system, and I asked you to determine if they're even and odd. And I'm sure it's tempting to say, okay, that's a 3, so this number ends with a 3, so it's odd. That's a 4, the second number ends with a 4, so it's even. But if we convert these to base 10, we see that the number represented here, the first one, is 58, which is even, right? So I've got a number in S20 that ends with a 3, and yet it's even, all right? Then this number, if I change this to base 10, is 49. So I have a number that ends with a 4, and yet it's odd. Okay, so this changes everything you ever thought you knew about the universe, right? If you can't just look at the last digit and tell whether a number is even or odd. So we need to examine here then, why does this not work? This rule that we've always known, it's a rule that works in base 10 but not in base 5. All right, so what makes it work? So in the add to your notes document, you were looking at all the divisibility rules for base 10, all right? Or not all of them, the ones that are the most obvious. There is actually a divisibility rule for 7, but it's so complicated that you might as well just go find a calculator and divide by 7, okay? So in the document from that you looked at, then when you took notes, you had rules for 2, 4, and 8. I'm going to kind of group those, 2, 4, and 8 in one grouping, and 3 and 9 in another grouping, and then 5 and 10 in another grouping. So the idea, though, behind explaining the divisibility rules is we need to consider this first statement. If 18 is divisible by 3, does that mean every multiple of 18 is also divisible by 3? So once I establish that 3 goes into a number, say n, does that mean that every multiple of that is still divisible? All right, and so this would, again, if we were in real class, this would be like on the board as a warm-up, right? And I would ask you to think about it, and I would hope you would notice that multiples of 18, like every single one of them has this 3 as part of it, because 18 is made up of 3 squared, right? So I'm never going to get rid of this 3 by multiplying by 18, okay? So the nth multiple of 18 is still divisible by 3. So that's going to help me down here explaining some of these rules, because once I establish that, say, a number is divisible by 4, right? That's going to mean that every multiple of that number is still divisible by 4. All right, and that's how I'm going to explain my divisibility rules. Another thing that I have to do to explain my divisibility rules is I have to think back to and really examine my my cube, right, which is 1,000, right? My flats, which are 100. Right, my longs, which are 10. So I want to think about what my base 10 blocks look like. And then I've got my unit. But if I think about taking a flat, this is 10, right? A 10 could be divided by 2. Agreed? Right? My flat could be divided in half, which means then if I establish that my tens place is always divisible by 2, that means that any multiple of 10, my flats, my cube, on and on and on and on and on forever and ever and ever, once I know that my tens place is divisible by 2, every multiple of 10 is still divisible by 2, which means that if I had some number that had a certain variety of longs, flats, cubes, everything would be divisible by 2 other than, right, whatever may or may not be in the units place. All right, so the divisibility of the entire quantity depends only on what's in the ones place. All right, and that's why I only have to look at the last digit to determine whether or not a number is divisible by 2. All right, so notice over in base 5, this is why this doesn't work in base 5. And again, I wish we were in class because you'd be talking with your partners about some ideas for what you think a divisibility rule for 2 would be in base 5. Because remember, this has 5 units. This is 25 units. Okay, so I can't just break this number in half, right? So what's in this second place here with the longs place, the long is not divisible by 2, right? And that's what in base 10, the fact that the long is divisible by 2, that's what in base 10 allows me to only look at the last place, right? Are my 1s divisible by 2? If they are, the whole number is divisible by 2. If not, then my number is odd. This place at the same time together, is this divisible by 4? All right, now for 8, 1,000 is divisible by 8, which means any multiple of 1,000, 10,000, 100,000, 1,000,000, those are all divisible by 8. 100, 10s, 1s are not divisible by 8. So that's why I only have to check the last 3 digits. So what do you think a rule would be for 16? Divisibility rule for 16. Okay, so if we were in class, I would ask you to extend this a little bit, right? And tell me what a divisibility rule for 16 would be. Okay, and for 16, you would check the last 4 digits. So you'd have to have a really big, long number. Check the last 4 digits to see if that number divisible by 16. All right, because 10,000 is divisible by 16, and any multiple would be, and so on and so on. Okay, so I don't expect you to know a rule for 16, but that's how I could keep going. I could say, well, what's a divisibility rule for 32, right? That would be if the last 5 digits are divisible, and so on. But again, that doesn't do me any good unless I'm working with enormous numbers. But the rule for 5 and 10 is very similar, right? The rule for 5 and 10 is for, we only have to look at the last place to see if it's divisible by 5 and 10. That's because my 10 is divisible by 10, obviously, and divisible by 5 also, okay? Meaning that it all comes down to what's in the 1's place. Okay, so for 10, I can't have any number of 1's that would be divisible by 10, right? So that's why for divisibility rule for 10, I have to end in a 0. I have to have no 1's, okay? But divisibility rule for 5, I could have 5 1's, okay? So I could extend my divisibility rules to a different base, and that's a bonus on the homework. Okay, like if I were working in, say, base 8, okay, and in base 8, this is 64, this is 8, right, and then I have my unit. So I could say, well, what's the divisibility rule for 8 in base 8? Okay, and in base 8, I'd have to have 0 units to be divisible, for my number to be divisible by 8, right? Because this is divisible by 8, right? What's a divisibility rule for 4 in base 8? And I could say, well, my longs place is divisible by 4. Therefore, my entire number in base 8 would be divisible by 4 if the units place was divisible by 4, right? So in other words, if I were in base 8, I am divisible by 4 if I end with a 0 or a 4. right? Since my longs place is divisible by 4, and then therefore all multiples of that are also divisible by 4. So I only look at the last place, the units place, all right? And I have to end with a 0 or a 4. All right, so if you can find a divisibility rule in another base, that's bonus on your collected. So let's take a look at a divisibility rule for 3. And I'm going to show this in 2 different ways. The first way is a little more concrete. The second way will be a little more abstract. So if I were to take each individual piece, okay, and I were to divide it by 3, if I take a long and divide it by 3, there's 1 left over, right? And if I take a flat and divide it by 3, I have 1 left over, right? And that happens at every single place. Okay, so what that means is if I were to lay out this number, 4,851, all right, that would be 4 flats, or I'm sorry, 4 cubes, 8 flats, 5 longs, and 1 unit. All right, I could divide each individual piece by 3. And if I took each one of my cubes and I divided them up into 3 cups, right, I would have 1 remaining unit from each cube. Okay, and if I did that with my flats, I took each one of those flats and I broke them apart and I put them all into 3 cups, I would have 3 units left, 1 unit from each flat. Or I'm sorry, 8 units. Wait, let me try that again. I would have 8 units left over because I would have 1 unit from each flat. Okay, so I'd have 8 units left there. I'd have 5 units left from my 5 longs. So when I'm adding the sum of the digits, right, what I'm really adding up is the sum of the leftover units, right? If my leftover units taken all together are divisible by 3, then the entire number was divisible by 3. Okay, so that's a more concrete way, concrete because I'm referring to the blocks. Here is a slightly more abstract way to look at the proof, this proof. If I were to take the digit A, B, C, D, is this divisible by 3? Okay, if I were to expand this out, that would be A times 1,000 plus B times 100. So I'm writing this in expanded notation. The C is in the tens place, and then the D is the ones. All right, is that divisible by 3? And I am going to write 1,000. I'm just substituting something for its equal, right? 1,000 is equal to 999 plus 1. All right, so I'm just substituting something for its equal, but in a useful way. I'm sorry, that should be a 99. Okay, then I am going to distribute. Okay, I'm going to distribute and then I'm going to group. Okay, so I'm going to do, A goes to here, A goes to here. And then I'm going to rearrange the order because I have a commutative and an associative property that tells me that I am allowed to rearrange my order. So back to a text box. So I'm going to write A times 999. So I'm going to group all the stuff with the 9s together. Times 9 plus, and then when I distribute, I would just get A times 1, B times 1, C times 1, and then my D dragging along at the end. Okay, so is this number divisible by 3? Well, if I were to look at this in 2 halves, right, this half in red is certainly divisible by 3. Okay, because 3 divides each term in the sum. Okay, so this is divisible by 3 for sure. All right, so then what it boils down to is this is what I don't know, is this divisible by 3? All right, and if it is, then the entire number is divisible by 3. Okay, so again, if the sum of the digits is divisible by 3, then the entire quantity is divisible by 3. Okay, so back over here, so you have to prove the 9 rule for collected 4. And again, it's very, very, very similar, and you can do it referring to the blocks, or you could do something like I just did with the ABCD. Okay, very similar to what I just did. But anyway, let's go back here to base 5. And what would happen if I took my long, because again, I'm trying to find a divisibility rule for 2 in base 5. Okay, if I took my long and divided it in half, I'd have remainder 1. Right? And then if I took my flat and I divided it in half, I'd have remainder 1. And if I'm in base 5 and I've got my cube, which is 125, if I divided it in half, I'd get remainder 1. And so again, I wish we were in class, because then I would say to people, well, when I divide each piece and I always get a remainder of 1, then I'm just looking for, are the sum of those remainders divisible by the number in question? Okay, so in this case, I'm looking for a divisibility rule for 2. Is the sum of these digits divisible by 2? If it is, then the entire number is divisible by 2. So in base 5, if I want to tell if a number is even, the divisibility rule in base 5 for 2 acts like the divisibility rule in base 10 for 3. Okay, so if I am in my S20 numbers and I want to tell if a number is even or odd, I have to look and see if the sum of the digits is divisible by 2. If the sum of the digits is even, then that base 5 number is even. If the sum of the digits is odd, then that base 5 number is odd. All right, so this is one of my favorite activities because, again, one of the things I like doing in this class is challenging some of the things that you've just always known but never really known why, right? And so by looking at a different number system where some of our very fundamental rules don't work anymore, then that really begs the question of why do these fundamental rules work for us in base 10?